Now that we have discussed about circle passing through 3 points, we have come with an interesting outcome that there's only one circle possible to be drawn through 3 non-collinear points. Now let's see the 3 non-collinear points and the circle through which we give a special case of a circumcircle. Today's session is about circumcircle, connecting with 3 non-collinear points in the plane. What is circumcircle? So let's see how circumcircle is defined. Let me take a triangle ABC and connect the circle properties with that triangle. So initially I take a triangle ABC. Suppose I take 3 non-collinear points . Say the 3 non-collinear points are A, B and C. So for these 3 points, we have already discussed that there's only one circle which can be drawn passing through these 3 points, non-collinear points A, B, C. So A, B, C are non-collinear points in a plane. So let me just join the points and see what kind of a figure we get. So here we get 3 points A, B and C. And these 3 non-collinear points, when I join, forms a triangle ABC. ABC is a triangle when each of its vertices are joined. And we know that ABC are the vertices of the triangle. So for any 3 non-collinear points in a plane, when we join, we get a triangle through 3 vertices A, B and C. So let's see how we define a circumcircle for this triangle. So by going through the 3-point theorem, we have only one circle which can be drawn passing through all this. Is how we get a triangle with only one circle passing through A, passing through B and passing through C. So we have a circle passing through exactly the vertices of the triangle. So any circle which passes through all the 3 vertices of a triangle is called a circumcircle. Circumcircle definition. A circle which passes through all the vertices of a triangle. For example, for this triangle ABC, this circle passes through the vertex A, vertex B and vertex C. So a circle which passes through all the vertices of a triangle is called a circumcircle. Is how I understand a circumcircle connected with triangle ABC. Here is the triangle ABC and here is the circle passing through the vertices A, B and C, and this is called circumcircle, connecting the triangle with the circle properties. Circumcircle connected with triangle. Now that we have discussed about circumcircle being a circle which passes through all the three vertices of the triangle, now comes the understanding of circumcenter. Circumcenter is the topic of the session. What is a circumcenter? So here we have a center, that means we are talking about the center of the circle. So clearly the circumcircle is very much connected with the circumcenter. So let's take the circle and understand the circumcenter for that particular circle. So let's take a triangle initially. So here I have a triangle A, B and C, and here I have a circle which passes through all the three vertices of the triangle. So here I have vertex A, vertex B and vertex C. Therefore, since this circle passes through all the three vertices A, B and C for the triangle, this is no doubt for being a circumcircle. Now clearly we identify the center of this circle as somewhere in this region of the triangle. So the center of this circle, which is clearly in the triangle at some region, is called the circumcenter, because this center of the circumcircle is connected with the triangle at this point. So circumcenter is identified to be the center of the circumcircle. So here this point is called circumcenter. Is how we understand the circumcenter for a given circle. So definition of circumcenter. The center of the circumcircle, the center of the circumcircle is called circumcenter. Is how we understand the circumcenter O out here is called the circumcenter for this circumcircle. So here point O is circumcenter. Center of the circumcircle is called circumcenter. Is how we understand the concept. Now that we have defined circumcenter, now comes the understanding of circumradius for a circumcircle. This session is about circumradius for a given circumcircle. So let's discuss about circumradius. Circumradius. What is circumradius? Let's take a circumcircle to understand the concept circumradius. So let's take initially a triangle ABC, for which I had to draw a circumcircle. So here I have a triangle ABC and then I have a circle which clearly passes through all the 3 points. In this manner is how the circle passes through all 3 points. And clearly we know that such a circle which passes through all the 3 vertices of the triangle is what we define as circumcircle. Now that we have defined circumcenter to be the center of this circle, say it lies somewhere here, then clearly I see that the distance of this center from the vertex A and from vertex B and from vertex C is same, because this is the center of the circle. The distance of the center from each of the vertices is same. That is, I have OA equals OB equals OC, because it is same radii, since same radii, and hence this equals this equals this, and that radius of the given circle is called circumradius. For circumradius is defined to be the radius of the circumcircle is defined as circumradius. So let's come with the definition. The radius of the circumcircle is defined as circumradius. Therefore, we define the radius of the circumcircle is defined as circumradius. Is how we define for a circle. The center of the circle, the center of the circumcircle is called circumcenter, and the radius of the circumcircle is called circumradius. And when we talk about the circumcircle, it's a circle which passes through all the 3 vertices of a triangle ABC. Is how we understand circumcircle, circumcenter, and circumradius. Now that we have discussed about various properties of circle connected with chords and radius and center and triangles, etc., now comes connecting the circle with perpendicular lengths. So initially, let's try to understand what do we mean by the perpendicular length or the perpendicular distance. This session is about understanding length of the perpendicular. Length of the perpendicular. So let's see how we understand length of the perpendicular through the geometrical means of understanding. Imagine I take a line L. Here is a line L, and then I have a point P out here. So now I would like to define the perpendicular length from P to line L. So if I drop a perpendicular from a point P up to the line L, I clearly understand that this gets dropped straight out here, exactly perpendicular. Say it drops at M. So here the length PM is called length of the perpendicular. So this length which we define from point P to the line L is called length of the perpendicular. So here I have clearly the perpendicular distance which defines as length of the perpendicular from point P to the line L is nothing but the distance PM which we refer. So this is how we define the length of the perpendicular. Length of the perpendicular from the point to the line L is how we understand length of the perpendicular. It's very important to note also that the length of the perpendicular is the shortest length from the point to the line. If I take different set of lines, the perpendicular length is the shortest. Let's see in brief how this becomes the shortest. Now that we have defined the length of the perpendicular, now comes what is the special case or what is the significance of the length of the perpendicular. How is it special as different from other lengths? Let's investigate the length of the perpendicular from a point to a line L. This session is about shortest distance from a point to a line. Shortest distance from a point to a line. I have a line and I have a point. Now as we can see, one of the perpendicular length is this, as clearly drawn out here. And there are other lines also possible from point P to the line L. Like we have different lines which I can draw from point to the line. Now clearly I can see that if this is M and this is L, Q, S, etc., I find that all the lines from P to L are a bit far away, but the shortest is the one which is straight drop perpendicular. So out of PS, PM, PL and PQ, I find PM to be the shortest because it is the perpendicular length. So my learning outcome here is that if the line is perpendicular length, then that line, that distance or that length will be the shortest, is what we make the learning outcome. Now because this is dropped at perpendicular, this is perpendicular, and therefore this makes me understand this is the shortest. So this is the shortest. This is the shortest length of all, is how we understand the shortest length of all is PM. So my learning outcome in this case is that the perpendicular length or the length of the perpendicular is the shortest length from a point P to a line L is how I make the learning outcome. Is how we make the learning outcome. The perpendicular length is the shortest length from a point P to a line L. So in this case, from a point P to a line L, the shortest length is this. Is how we understand the shortest length connected with length of the perpendicular or the perpendicular length. PM is the shortest length in this case. Now that we have discussed about length of perpendicular and various other properties of circle, now let's see a property which connects the chords and their distance from the center. Distance of the chords from the center is how we understand the distances. So this is about connecting the chord properties with their distances from the center. Chord properties. So let's see the property which says that if I take two equal chords in a circle, then the property says that those equal chords will exactly be at equal distances from the center. So let's make a statement and understand the concept geometrically through a circle and equal chords. So here I have a statement: equal chords of a circle are equidistant from the center. Equal chords of a circle are equidistant from the center of that circle. Is how the statement comes out. How do we understand this statement geometrically? The statement says equal chords of a circle are equidistant from the center of that circle. So here the condition is equal chords will be equidistant from center of that circle. So let's see geometrically to understand this concept. So here I have a circle. Here is my circle and I have two equal chords. Say, here is my chord and here is my other chord, and both the chords are of equal length. So AB is the chord and CD is the chord for this circle in such a manner that they are equal. AB and CD are chords such that they are equal chords. So this equals this is how we understand the equal chords. Now we have to show that they are equidistant. So clearly the property says that if this is the center of the circle, then the distance from this point to the line is perpendicular length. So here comes the perpendicular length from the center to M N. So here I have OM and ON which are equidistant. So the property says that for this circle which has equal chords AB and CD, they are equidistant from the center. That is, the distance of O to AB, which is OM, will also be equal to the distance of O from CD, which is n, and they are equal, is what the property says. They are equidistant from the center. So here OM equals ON. That is, they are equidistant from the circle, is how we understand the property. So in this case, AB, distance of center O from chord AB is equal to distance of center O from chord CD, is how we understand the property. The distance of the center from chord AB is equal to distance of center O from chord CD, simply because the two chords are equal. AB equals CD. If the chords are not equal, then they won't be of equal distances. This property holds only when the chords are equal. Now that we have discussed the property, let's try to investigate the converse. The converse of the chord property as discussed in the previous session. So let's see the converse statement. So here we have the converse holding true. That is, the statement for the converse says, if the chords are equidistant from the center of the circle, then the chords will be of equal length. This is how we understand the property. If the chords are equidistant from the center of the circle, then the chords will be of equal length. They must be of equal length. This is how we understand the converse. Let's see geometrically the property. This is the circle, this is the center, and I have two chords. AB and CD. Now these two chords are exactly at equal distances from the center O. The two chords are equidistant from the center of circle, then the converse says the chords must be of equal length. Now these are equidistant, therefore the chords must be equal. So here I take OM equals ON. O is center of circle and AB and CD are chords of the circle. And it is given that they are equidistant, so OM equals ON, since they are equidistant from the center. Then the converse says under these three conditions implies the two chords must be of equal length. The length of the chord AB must be equal to the length of the chord CD. So I write this in this way, that length of the chord AB is equal to length of the chord CD. So is how we understand the converse. If the chords are equidistant from the center of the circle, then the chords must be of equal length. AB equals CD in this case. Converse holds true for chords. Now that we have discussed about various chord properties in a circle, now let's discuss about angle subtended by an arc. So we have this property which we need to understand through various properties connecting angle subtended by an arc of a circle. Let's see what is meant by angle subtended by an arc of a circle. Let's take the session. Today's session is about angle subtended by an arc of a circle. Angle subtended by an arc of a circle. Let's take a circle to understand the angle subtended by its arc. So here I have a circle, and then I have a center. So for example, the arc from A to B is how I take. So I take the part of the circle that is an arc from A to B, and I want to know this arc AB of the circle, what angle it makes with the center. So angle subtended by an arc of a circle is understood to be the angle made by the arc with respect to the center of the circle. For example, here is the arc AB. Now this is the angle as made by the arc with the center of the circle. Is how we understand the angle subtended by this arc AB with its center is this. So this angle is referred to as the angle subtended by an arc of the circle. So here this is angle subtended by the arc AB. So here when I take the center O and I take the arc, then the angle at which the end points of the arc converge is what is called angle subtended. So here is the end point which connects, and here is the other end point which connects, and hence we get an angle. So theta is the angle subtended by the arc AB at the center of the circle. Angle subtended. So here I have the definition. Angle subtended by an arc of a circle. Let's see the definition. The angle made by the arc the angle made by the arc with its center is called angle subtended by the arc of the circle with its center is how is understood to be angle subtended by the arc of the circle at its center. It is not compulsory that the arc subtends the angle only at the center. Say for example, I take a point P and I would like to understand the angle subtended by this arc AB with respect to this point P. So I understand this as joining this, and here I get the angle subtended by the arc AB at point P. So whatever is the point, if the endpoints of the arc meet at that point, then the angle formed by the endpoints of the arc with that point is nothing but called the angle subtended by an arc of a circle with respect to that point. P is the point here and O is the point here. Here is the angle subtended at O by the arc AB, and here is the angle subtended by arc AB at P. So this angle refers to angle subtended by the arc AB at point P on the circle is how I understand the concept of angle subtended by an arc in the circle with respect to its point. Now let's try to investigate the connection between the chords and the arcs. So this session is about connecting the lengths of chords and lengths of arcs. So let's see how we can connect the chords and the arcs. Chords versus arcs. So here the property says that if I take two equal chords for a circle, then the two arcs will be of equal length, the arcs made by that chord. Let's see how the property holds. So here the property says that if I take a circle, if I take two equal chords, say AB is the chord and here CD is the chord, such that they are equal. Now clearly for these equal chords they make certain arc length out here. So this is the arc length as made by the chord AB, and this is the arc length as made by the chord CD. So the property says that the arc length as made by the chord AB will be equal to the arc length as made by the chord CD, simply because the two chords are equal. That means the circle property says that if two chords are equal, then they make equal lengths of the arcs. Chord AB is equal to chord CD, that implies arc AB is equal to arc CD, or they are congruent, is how we understand the property. Two chords of equal lengths make two equal arc lengths, is how we understand the property. In the statement, the property says two chords of equal lengths make two equal arc lengths. Is how we understand the property. In the statement, the property says two chords of equal lengths make two equal arc lengths. Is how we understand the property. In the statement, the property says two chords of equal lengths make two equal arc lengths. two chords of equal lengths make the two arcs make the two respective arcs equal. In other words, they make them congruent, equal in all respects. So here the property says two chords of equal lengths AB equal to CD implies the two chords of equal lengths make the two arcs, the respective arcs, to be equal. So if chord AB equal to chord CD, then length of arc AB will be equal to length of arc CD. That's how we understand the property. Connecting chords with arcs. A chords connected with the arcs of the circle. Now that we have discussed a property connecting the chords and the arcs, if the lengths of chords are equal, then the respective arc lengths are equal. Let's see the converse. What if the arc lengths are equal? Will the chords formed by those arc lengths also be equal? Is the question out here. So let's see if the converse holds true. This session is about converse of the previous theorem. So let's see the converse. Statement. If two arc lengths are congruent, if two arcs are equal, more importantly, if they are congruent, then the respective chords formed by those two arcs will be of equal length. Is how we understand the statement. If two arcs are equal, or they are congruent or equal in length, then the respective chords formed by joining the endpoints of the chords of the arcs to form a chord, respective chords formed by those two arcs will be of equal length. This shows that the converse holds true. That is, converse holds true. When I take geometrically, I understand that if I have a circle, if I have two arcs, say AB and CD, which are equal in length, AB which are equal in length, that is this arc equals this, then the chord as formed by AB and the chord as formed by CD must be equal, is what the property says. Arc AB equals arc CD implies the length of the chord AB must be equal to length of the chord CD. Converse holds true for the previous session. Given the statement, if two arcs are equal or congruent, then the respective chords formed by those two arcs will be of equal length. Converse holds true. Now that we have discussed about angles subtended by an arc of a circle, let's connect with what happens if the two arcs are equal. Will they subtend equal angle at the center? This session is about investigating angles subtended by equal arcs of the circle. Topic of the day: angles subtended by equal arcs of the circle. Angles subtended by equal arcs of the circle. So let's see how it comes. So here let's take a circle. Say I have two arcs which are equal in length. Say for example, I have a circle where I have the arc AB and the arc CD. Now here, if I have this arc being equal to this, that is arc AB is equal to arc CD, then in that case the property says that two arcs which are equal in length subtend equal angle at the center. That is, if the angle subtended by the arc AB is this and the angle subtended by the arc CD is this, then the property says that this angle subtended by arc AB will be same as the angle subtended by the second arc CD. That implies angle AOB is equal to angle COD is what the property says. If the arcs are of equal lengths, their subtended angles will also be equal, is how I understand the property for angles subtended by equal arcs of the circle. Let's write the statement in words. So here the property says that two arcs of equal lengths subtend, or arcs of equal length subtend equal angles at the center of the circle, is how I understand the property connecting the arcs and the circle. So my learning outcome in this property states arcs of equal lengths subtend equal angles at the center of the circle. The arc AB equal to arc CD implies the angle AOB is equal to angle COD, is what the property states. Let's see the next property connecting the arc and the subtended angle. This is one of the most important property in the circle properties connected with arcs. We use this in many solve mathematical problems which are solved using the connected properties. This session is about connecting angle subtended by the arc at the center and at the circumference of the circle. So here comes arc properties. So here the property says, let's take a circle. And let me say AB is the arc. So here for the circle AB is the arc. Now for this arc AB, the property says that angle subtended by this arc AB at the center, say this is the center, angle subtended at the center by this will be double the angle subtended by the same arc at any part of the circle. Say the arc subtends some angle at any part of the circle from here to here or down anyway. So let me pick a point P on the circle. So the angle subtended by this arc at P would obviously be when I join PA with PB. Is how I get. So here O is the center and this is called angle subtended at the point on the circle, which is this. So the property says that if the angle subtended at the circumference is theta, then this will be obviously double of that angle always, is what the property says. Any angle identified on the circumference is said to be connected with this in such a manner that if this is 30 degrees, this will be 60 degrees. If this is 40 degrees, this will be double of 40, which is 80, is how it goes on and on. So here the property says that implies angle AOB is twice of angle APB, is what the property says. Angle subtended at the center of the circle is double the angle subtended at any point on the circle. P is a point on the circle. So my statement says angle subtended by the arc at the center of the circle is double the angle subtended. The angles subtended by the arc at the center of the circle is double the angle subtended by it at any part of the circle. So here P is on any part of the circle, at any part of the circle, is how we understand the double angle property of the circles. Angles subtended at center and on the circle are related to angle AOB is twice of angle APB, is how we understand the concept. Now that we have discussed one of the most important property in circles, angle subtended at the center of the circle is always twice that of angle subtended by the same arc at any point on the circle or any part of the circle. Let's see some other extended properties which are useful in solving many math problems connecting with geometry. This session is about connecting the angle property with the segments. So here angle property in a segment of a circle. Angle property in a segment of a circle. So let's see how the angle property is connected for the segment of a circle. We have already discussed that a segment is a line or a chord which divides the circle into two regions. Say, for example, I have a circle and I have this. Then clearly we know that AB is the chord which divides the circle into two regions, region 1 and region 2. Therefore, this is called major segment and minor segment. So here we have the segments as divided through a chord. So angle property in a segment of a circle says that if I take the chord AB and I take the subtended angle made by the chord AB. Suppose this is the angle as made by the chord AB with point P, and there's another point, say Q, and say the chord AB subtends an angle at the point Q. Say for example, this is the subtended angle for the chord AB at Q. Is what we get. So angle APB and AQB are said to be angles in the same segment. So APB and angle AQB are called the angles in same segment. So APB and AQB are called angles in same segment, is how we understand the two angles. So let's see how the property connects the angles in the same segment. The property says that angles which are always in the same segment are equal. So if this is theta, this will be equal to theta. So these two angles being angles in same segment implies angle APB is equal to angle AQB, is how we understand the angles in the same segment. APB and AQB are the angles in the same segment. So property connecting this. Angles in the same segment are always equal. Angle APB equal to angle AQB because they are angles in the same segment. Angles in the same segment are always equal, is how we connect the property. Now let's see the converse of the previous session. The property which says angles in the same segment are always equal. This session is about converse of the made statement. The converse of this session is very interesting because I can prove that I can draw a circle with the same segment property. That is, if I have a line AB this is the line AB, and say there are two more points P, or I take this to be C, and here is another point D, such that this line segment makes equal angles or subtends equal angles at this point. So the property says that if the chord AB subtends angle C with theta, then also if the chord AB subtends an angle, same angle at D, then the property says that if these two are the same subtended angles as made by the line segment AB with respect to C and D, then it is perfectly possible to draw a circle passing through all the 4 points. That is how I get a circle, is what the property says. If AB is the line segment and ACB angle is equal to angle ADB, that implies ABCD are concyclic. Concyclic in the sense they pass through the circle. All 4 points pass through the circle. That implies ABCD are concyclic. That is, they all pass through the circle, is how we understand the concyclic property of A, B, C and D. So here my converse property says that if a line segment AB subtends equal angles at C and D, in the plane, in this plane, then the points A, B, C, D are concyclic. That is, they all pass through the circle, is how we understand the property connecting the line segment which makes equally subtended angles and hence pass through the circle, connecting with concyclic with equal angle subtended, the converse of the segment theorem. This session is about cyclic quadrilateral. Now that we have seen many triangles where we can draw a circle passing through all 3 points, which is called circumcircle, we have already discussed about circumcircle, which is formed by joining all the 3 points of this triangle through a circle. So in such a case, now comes just like the triangle where a circle is drawn connecting all 3 points. What about a quadrilateral? Can we draw a circle passing through all the 4 vertices of the quadrilateral? Is what is the investigation. So investigating the quadrilateral versus circle. So let's see how we can relate a circle with a quadrilateral. For example, I take a quadrilateral A, B, C and D. Now, just like a triangle where we can draw a circle passing through all 3 points, it is not possible that every quadrilateral can be made to pass through the circle. There are only few quadrilaterals which have a circle formed exactly with all the four vertices. So we have a special case in which the difference comes that at least one circle, there is only one circle which passes through A, B and C is how we understand the triangle, and that circle is called circumcircle. But in case of quadrilateral, there may be a circle passing through A, B, C and D, but not always. Only few quadrilaterals have the circle exactly connecting or touching A, B, C and D. So this is one thing where we have a special case of a quadrilateral, that quadrilateral which is taken into consideration, which passes through all the four vertices, a circle which passes through all the four vertices. So let's take the special case of a quadrilateral, only that quadrilateral which exactly fits in the circle. This session is about cyclic quadrilateral. What is a cyclic quadrilateral? It is very simple with the definition itself, which says a quadrilateral which is cyclic or which forms an exact circle. So in most simple manner, we can define a cyclic quadrilateral to be a quadrilateral which can exactly fit in the circle, any circle of different radii. So for example, I take a quadrilateral which can exactly fit in out here. So the quadrilateral ABCD clearly fits in this circle, and hence this quadrilateral is called cyclic quadrilateral. Because it exactly fits in the circle. Since it exactly fits in the circle with center O, is how we understand cyclic quadrilateral. So if I take this in the statement, quadrilateral a quadrilateral whose vertices pass through the circle is called a cyclic quadrilateral. That's how we understand a cyclic quadrilateral. A quadrilateral whose vertices pass through the circle. ABCD is a cyclic quadrilateral because all the four vertices A, B, C and D pass through a circle. Or in other words, this quadrilateral ABCD exactly fits in the circle, and hence such a quadrilateral is called a cyclic quadrilateral. Every quadrilateral is not cyclic, only few of them fit exactly in the circle, is how we make the learning outcome. Cyclic quadrilateral. Now that we have discussed about cyclic quadrilateral, let's see some of the geometrical properties connected with those quadrilaterals which are cyclic. This session is about connecting the cyclic quadrilateral with its properties. Properties of cyclic quadrilateral. Let's see how we can do it. Properties of cyclic quadrilateral. Suppose I have a cyclic quadrilateral ABCD. So the quadrilateral ABCD is a cyclic quadrilateral. Then the property says that for a cyclic quadrilateral ABCD, the opposite angles always are supplementary. This and this are supplementary. So property says for a cyclic quadrilateral ABCD, angle A plus angle C is 180 degrees and angle B plus angle D, which are opposite angles, are always supplementary. So this plus this is 180 and this plus this is 180. So my other pair is how we understand the property. For a cyclic quadrilateral, sum of these two and sum of these two will always be 180 degrees. So we have the property which says opposite angles of a cyclic quadrilateral are supplementary. So opposite angles of cyclic quadrilateral are supplementary, that is 180 degrees. Is how we understand the supplementary and the complementary of the cyclic quadrilateral. Let's see the converse of the previous session. If the pair of opposite angles of a quadrilateral is equal to 180 degrees, then will the quadrilateral be cyclic? This session is about the converse of cyclic quadrilateral property. So the property says that if there exists a quadrilateral A, B, C and D such that the opposite angles A, B and D and A and C sum up to 180, that is, for a quadrilateral ABCD, angle A plus angle C equals 180 and angle B plus angle D equals 180 implies the property simply says that if the sum of opposite angles is 180 degrees, then the quadrilateral must be cyclic. All the four vertices must pass through the circle is how we understand the cyclic quadrilateral properties. That implies quadrilateral ABCD is cyclic, is how we understand the converse of the previous property. In general sense, my property says if the sum of opposite angles in a quadrilateral is 180 degrees, this and this being opposite angles, A and C are opposite, B and D are opposite angles of a quadrilateral. If the sum of opposite angles in a quadrilateral is 180 degrees, then the quadrilateral must be cyclic. There's no chance, there's no way, but the quadrilateral in that case must pass through all the four coordinates of the circle. Must pass through all the four coordinates for the cyclic property. Cyclic property holds true for the converse. Converse of cyclic quadrilateral property. Now that we have discussed about cyclic quadrilateral properties and including its converse, now comes the new property which connects internal angular bisectors of a quadrilateral. So let's see the quadrilateral which is formed by internal angular bisectors of the quadrilateral. This session is about internal angular bisectors of a quadrilateral. Quadrilateral and its internal angular bisectors. So let's see how this is connected with the cyclic quadrilateral. So let's take a quadrilateral to understand the concept more better. I have a quadrilateral ABCD. Say ABCD is a quadrilateral. Now for this quadrilateral, let me take each of the internal angular bisectors. Say for example at A, the internal angular bisector is this, and at B, the internal angular bisector is this, and at C, the internal angular bisector at B, and let's take an internal angular bisector at C. And an internal angular bisector at D. Say here I have a quadrilateral which is formed by each of the internal angular bisectors of A B, C and D. So this quadrilateral which is formed by each of the internal angular bisectors, let me denote by P, Q, R and S. So the property says that such a quadrilateral which is formed by each of the internal bisectors, angular bisectors, will be cyclic. That means a quadrilateral which is formed out here which is PQ RS must be cyclic. It has to pass through a circle as what the property says. So this quadrilateral must be cyclic quadrilateral is what the property says. The quadrilateral which is formed by each of the internal angular bisectors of the actual quadrilateral will be cyclic is the property which connects quadrilateral and its internal angular bisectors. The property which says the quadrilateral which is formed by the internal angular bisectors of here it is PQRS which is formed by the internal angular bisectors of quadrilateral ABCD will be cyclic. So this quadrilateral which is formed by internal angular bisectors is cyclic. So this is the property cyclic quadrilateral connected with internal angular bisectors.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.